Hi guys. In the last video we took a look at stationary points and how to locate them for a function and identify their natures. And that's the most recent in a line of skills that we've learnt in regards to functions throughout this year. We know how to find y-intercepts, x-intercepts. We can now locate the points on curves where we have local maxima and minima. And all of this information together allows us to do a pretty good job of quickly sketching any curve, regardless of whether we've actually seen it or the level of complexity. Obviously, we've got tools that can do that for us. We've got graphic calculators, we've got websites like Desmos where we can input a function and see the graph. But it remains a really important skill in mathematics to be able to just look at the equation for a function and to be able to kind of picture it in your head, or at least work out basically what it looks like. And that's what we're going to work on today. So curve sketching is the culmination of a variety of skills that we've learnt this year, from x and y intercepts, domains and ranges, asymptotes to the most recent stationary points. We'll start with the function f of x equals x cubed minus 3x plus 2. And the first thing that we can look at is what is the y-intercept of this function. And we remember that we find the y-intercept by looking at the value when x is 0. So the function at 0 is 0 cubed minus 3 times 0 plus 2, and that equals 2. So that gives us one of our points, and that is that the function passes through the point 0, 2. We can then look at x-intercepts, and they're a little bit harder. We find those by setting the function equal to 0, x cubed minus 3x plus 2. Now, because we're dealing with a cubic, the best way to approach is sometimes to just try different values. And we know that if we test a value in our function and it comes out equal to 0, that we've found one of the x-intercepts. So we'll try the function at 1. And we've got 1 cubed minus 3 times 1 plus 2. That's 1 minus 3 plus 2 is in fact 0. So we know that we have an x-intercept point at 1, 0. Now we can use polynomial division because we know that x minus 1 is a factor. Okay, and therefore our function f of x is equal to x minus 1 times something. So we'll come over here and we'll just do that quickly. So we've got x cubed minus 0x squared, so plus 0x squared, minus 3x plus 2, and we're dividing into that x minus 1, and so we can see that we're going to need an x squared term, and that'll give us x cubed minus x squared. Subtracting that away, and we're going to get plus x squared. Bring down the minus 3x. Okay, and we're going to need a plus x term. That'll give us x squared minus x. And subtracting that away, we'll get minus 2x. Bring down the plus 2. And we're going to need a minus 2. And that'll give us minus 2x plus 2. Which we knew already would give us 0 because we knew x minus 1 was a factor. Okay, and so that gives us the rest of this function now in its factorized form. We've got x squared plus x minus 2. And we can factorize that out further and say that our function is x minus 1. And if we look, we need two numbers that multiply to give negative 2 and add to give plus 1. And we'll get that with x equals plus 2 and minus 1. What we've got there now is a repeated factor. X minus 1 appears twice. So we know that there's actually only going to be two x-intercepts for this function. And one of them is going to be a point where the function just touches and then turns back up again. So it doesn't actually cross the x-axis there. so we remember that from first semester. What we've got though now is the rest of our x-intercept points. So we know we've got one at x equals 1, and we now know too that we've got one at -2, 0 is the other point. So if we were to start graphing at the moment, we've already got 3 points to put on our graph. We know where it crosses the y-intercept, and we know where it crosses the x-intercept at -2 and touches the x-intercept at 1. We can now use, though, our new maths, looking at turning points, to work out what's going on with the rest of the function. So what we're after now are stationary points. And for those, we are going to need our derivative function, f dash x equals 3x squared minus 3. And of course, stationary points have derivatives equal to 0. And that means that 3x squared equals 3, x squared equals 1, and x, therefore, equals plus or minus 1, the square roots of 1. We already knew that x equals plus 1 would have to be a turning point, because we knew that the function comes down, touches that point, and turns up again. But now we know that there's also a turning point at x equals minus 1. And so, as we did in the last video, we need to finish off by working out what the natures of those points are. Drawing up our table, we already know that -1 and 1 have derivatives of 0, and we pick 3 other values around these, so we're going to choose -2, 0, and 2. Now the derivative function 3x squared minus 3, when x is -2, we're going to have x squared is 4, 3 lots of that is 12, minus 3 is 9. When x is 0, that's just simply going to come out -3. And when x is 2, we're going to again have 3 lots of 4 is 12 minus 3 is 9. What that tells us is that our function is positive before x is -1, goes 0 at x is -1, negative in between, 0 again at x equals 1, and then positive afterwards. So we've identified that x equals -1 is a maximum of the function, and x equals 1 is a minimum. All we need to do now is substitute these values into the original function to work out the points. And in fact, we already know that at x equals 1, the function evaluates at 0, as well as the derivative. And all we then need to do is work out what the function is at -1. So that's -1 cubed minus 3 times -1 plus 2. -1 cubed is -1. 3 lots of -1 is -3, minus -3 is plus 3. So we're 2 plus 2 is 4. So that means that our turning point, our maximum value, local maximum, is at -1, 4. That gives us now 4 points that we can put onto a function and start to sketch out what our graph actually looks like. So we'll quickly recap. We have a y-intercept at 0, 2. We have x-intercepts at 1, 0, and -2, 0. We have a maximum at -1, 4, and a minimum point at 1, 0. Plotting those up, we've got our y-intercept at 0, 2. We've got x-intercepts at -2, 0, and 1, 0. And we know that the point -1, 4 is a maximum, and 1, 0 is a minimum. And so what our function is going to look like is this. It's going to come up through that point, curve over at the point -1, 4, come down through the point 2, 0, just touch and turn up at the point 1, 0, and then continue off. If we wanted to, we could substitute other values into our curve and work out other points and be more precise and have more guides to be able to draw that accurately. But the points that we work out here are the best ones to give us the most information quickly. Alright, so intercepts and turning points allow us to fix those key points where the function is changing greatly. If we apply this procedure to any function that we're given, we can fairly quickly come up with a highly accurate sketch of that function.